Yeah, Grace, thanks a lot. Although you can tell by the handwriting, it definitely wasn't me who graded it.
Well, yeah, you can tell that.
Did you write the numbers?
Nope, that was not me. Yeah, if you can read it, it probably wasn't me. I will post answer key. I don't think I remembered to do that this morning. I did for linear. It was up there, but for this class, I think I forgot. So I'll do that after class.
Are they more important?
Yes.
Those are the ones I had I typed in first. I just didn't remember. I think I forgot this one. All right. Questions about anything? Not Michael. Any questions about anything?
Wait, I have to show you now because I have to go to Dr. Roth's class after.
You can show me later.
You're going to be gone by the time I get done with class.
No, I will not be gone by the time you're done with class.
I'm done with class at 3.
I probably will still be here at 3.
You usually leave at like.
I will be here at 3.
And over here tomorrow. Say you're.
I will be here tomorrow, actually.
Oh, for scholarship day?
Math counts, yeah.
Presidential
I'll
call.
be here for actually.
And then I'm going to the basketball game tomorrow. Basketball games tomorrow.
I wasn't picked to interview people for classes.
That's really weird.
Yeah.
Well, the honor students usually have a whole bunch of different honor students.
That's the presidential scholarship.
And I'm sure.
I'm not cool enough to be a president.
They might have asked. They might ask the juniors and seniors who are actually. Yeah. Yeah. But apparently, Dr. Hartsock wasn't hard enough for help. Because usually he's really hard up for getting people to do it. So. Yeah.
There was not very many emails.
He emailed us about the form literally 1 week in advance.
Actually, he did it twice. One was quite a bit in advance, and the second one, he missed it.
Gotcha. All right. Well, I don't know anything about it. All right. So let's talk a little bit more about confidence interval stuff. Were we okay with the confidence intervals for means that we talked about last time with both the Z's and the T's and when to use them? Is that okay? Well, not just less than 30. You also have to have an unknown variance. If you know the variance, then you still use Z. Correct. If you still know the population variance, you still use the Z, even if it is small. Yep. Mm-hmm. Yep. All right. So let's do the next section then, which is still confidence intervals. Yeah, confidence intervals. All right, so in this case, we're going to do difference of means. No. Well, you have to calculate your standard deviation differently, but no. The big answer is no.
Obviously, I didn't do that hint on the homework, so I forgot about that 25 thing we did.
The integer correction thing?
Vessel's correction.
Huh?
Vessel's correction.
Okay. I haven't heard it called that before, but sure. That's certainly possible. Oh, I would not go by Wikipedia.
Wikipedia is becoming more trustworthy, Dr. Joe.
That's because they have Wikipedia edit-a-thons now. At the joint mathematics meetings back in January, they had a whole Wikipedia edit-a-thon there with grad students and faculty.
So they just like edited math things?
Mm-hmm. Yep, they sure did.
That sounds very good.
I didn't do it. I wasn't there. And even if I were there, I wouldn't do it. Because that doesn't sound interesting at all. I just don't use Wikipedia. So.
WikiHow.
WikiHow? All right. So when we did the confidence intervals for one mean, we used this idea, all right? Perhaps. Well, I hope you use that idea. Recall. All right. So, where did this part come from? What?
Large or bare?
No, just this part. This piece. What is this?
What is it?
Mhm.
It's sigma open skirt.
Thanks. You've been sitting next to Michael way too long.
I spent too much time.
What is this? Don't tell me single over square edge.
Should we write it down?
It's a standard deviation, right?
Yes.
It's a standard deviation of what?
This is
Population.
What is it the standard deviation of again? Which distribution is it the standard deviation of?
Normal. Oh no.
Which random variable is it the standard deviation of?
X. I've got a 1 in 26 chance. I already said Z, so it's the that.
I'm sure.
Is it the normal distribution?
That's what we're using to that's what we're using to get the interval. But I'm just asking, what is that what distribution? What random variable is that the standard deviation of? The distribution of X bar. Thank you.
We said this. Didn't we say that?
No. So this is the standard deviation of the distribution of the sample means, right? All right, so if we're looking for trying to get a similar idea for a difference of two population means, well, what do you think we're going to have out in front, do you think? Okay, but how many X bars do you think we'll use? Probably two of them, right?
I literally have. And he's got the time for you.
I did have the time for when we started, or at least when I opened that page. All right, so we have an X1 bar and an X2 bar, right? To use as our sample difference, if you will. All right. If it's normal, or if we have large enough samples, we're still going to use our Z sub alpha over 2 as our boundary points on the standard normal distribution. The reason why is because what? If we assume that, say, if we assume that the distributions of X1 and X2 are normal, then what can you say about the distribution of the difference? Still normal, right? And so if the difference is normal, and then the sample means are going to be, the distribution of the sample means will also be normal, so that difference will be normal, right? Difference of normal is still normal, right? So if we have normal distributions that we know about, or if we have a sample size large enough, our sample means distributions will still be normal, and differences of normals is normal. Right? All that good stuff? All sound familiar? So what we need is this piece, the standard deviation piece, to go in here. That's the piece that's missing, right? So let's think about what the standard deviation has to be if we were doing the sample means. Well, what is the standard? What's the variance of X1 bar going to be? Okay, so it'll be your sigma 1, whatever that happens to be, sigma 1 squared over n, because I'm doing variance, right?
Are the ends going to be the same for each, or are they going to be?
What do you think? I didn't say what you wanted, I said what do you think? Different, yeah. You might have different sample sizes, so let's say it's M, right? You're taking a sample size of size n from the first population and m from the second one. So those don't necessarily have to be the same. But those would be the two variances, right? If I have a sample size of n from x1 from population 1, and if I have a sample size of m from population 2, Let's do the variances. So if I want the variance then for the difference of the two means, what would that be? Yeah, we have to add them. Good. So what does that make the standard deviation? The square root of that, right? So that's what's going to go in where I put those little braces. Your book uses, I can't read the subscript without my glasses. Why do they use a W? Good question. I don't know why. So they use a sigma sub W. I think they let the W be the x1 bar minus x2 bar as the square root of this. So then this just goes sigma W up here. All right, so if your population variances are known, then this is what you're going to use for your standard deviation. You'll use the square root of the sum of the individual variances. This is not a huge surprise because that's how you calculate the variance. By the way, what property of the populations did we use to know that it's just a simple sum here for the variance? Yeah, it's independent, right? They have to be independent populations. If they're not independent populations, then there would be a covariance piece on the end. We're not going to worry about that. We're going to assume we have independent populations. But independence is necessary for that part, right? Or at least, I shouldn't say independence is necessary. I should say that covariance of zero is necessary. Independence implies covariance zero, but not necessarily the other way around. It wasn't on the phone. If you have it fine. Well, you have to know about independence and covariance, so you never know. All right. So this again assumes that the variances are known, probably not going to happen in practice, right? Why would, if you know the variance, you probably knew the mean, so why would you be doing this anyway? For funsies, okay? So if you knew the variance, then you probably knew the mean, so why would you bother doing it? So what we're going to talk about for the rest of this section, and it's going to be really for the small sample part, we're going to talk about what happens if we don't know what those are. Now again, if we know that the sample sizes are large, then we can go ahead and just replace those with your sample size, the sample variances, and call it good, just like we would otherwise, right? If the sample sizes are large, we know that we can just replace these with our sample variances and get a pretty good approximation for it. Because again, the sample variance is an unbiased estimator for the population variance. So if it's large enough, it should be pretty close. Because again, the variance of that's going to go down the larger the sample size is. And that's the whole idea. So this idea will be what you would use if you have large sample sizes. What happens though if the sample sizes get small? All right, so that's the idea here. So, and that's really the big issue. So there's a couple of issues that go along with it. So we'll derive what we're going to do for one of the issues. So one of them is that one of the issues that we can get around is what if we assume that the population variances are actually the same? Well, then we can do something that helps us out. Now, again, whether or not this is a valid assumption is up for debate. And we'll talk, this is something that we'll talk about later on, about how we can test if this assumption makes sense or not for the scenario. Okay? So we're not going to do it right now, but this is something that we can test for later. If you've done some more statistical testing above just doing, if you've done some hypothesis testing in other classes above just doing means or population proportions, there's something called an F test that you can do, and that's one of the things that we'll be talking about. All right, so what happens if the two are the same? Well, then what kind of distribution does the following have? Oops. I'll use sigma. I'm using x and y as opposed to x1 and x2 now, but that's okay. I think it's probably pretty clear by context what I'm doing. So I'm going to use sigma just for the common standard deviation, so sigma squared for the common variance. What kind of distribution is this? Well, I'll use the z, so it's probably what? Yeah. All right, it's probably normal. So again, the assumptions that we're using here is that our underlying distributions are normal. Right? If they're not normal, then there have to be other things that we do. In particular, later on in the semester, we'll do what are called some non-parametric tests on things. And in particular, we will, instead of trying to get a bound for the mean, we'll do some things about the median. Try to get a handle on what the middle is on other types of distributions that aren't normal, or at least aren't symmetric. It's just that. Mode usually just talks about the shape of the distribution, or the high point of the distribution is usually what we're looking for. So helps you a little bit with skewness, this kind of thing. But that's about it. All right. So if we have random samples, then let's look at the following. What kind of distribution does this have? -1. If we do this one, oops, this should be a sigma. Okay. All right, so if we do random samples, what should be true about those two, if I think about them as random variables, what should be true about those two random variables if we're doing random samples? What should they be? They should be independent, right? We agree? Those two things should be, if we're actually doing honest to goodness random samples, the x, if we assume that the x and the y populations are independent, then these two things should be independent of each other. The important part of that is that if I take, the book calls it a U, if I take these two random variables and add them together, so this is why we needed the independent part. If I add two chi-squared distributions together, what kind of distribution do you get? Seriously, Grace? Seriously?
This is why you can't be high school, because then you feel the need to get rid of that.
I told you I hang around my bookmark.
Uh-huh. Yes. All right. Is chi-squared, what do you do with the degrees of freedom? Add them. So how many degrees of freedom do you get? Minus the 2?
I told Dr. Olson that.
What? Yeah, what'd she say?
Well, we're talking about Euler.
Mm-hmm.
And
She did. Euler? No. Whitelid?
Dr. Often like that one.
No, I'm not surprised. All right. So I've got a standard normal z and a chi-squared u. So what kind of distribution can we make from a normal distribution and a chi-squared distribution? A t, good. So if we do t, if I do z, the normal on top, divided by, what do we divide by to make a t?
Square root,
Okay.
chi-square root, divided by. It's almost like you set it up.
All right. I'm not going to go through all of the algebra, but you can show that this becomes on top. You get your x bar minus your y bar, and then minus the difference of the two means. And on bottom, you'll get something that looks a little bit ugly. You'll get n minus 1, and then the variance for the first one, and m minus 1, variance for the second one, over n plus m minus 2. And I'll multiply this by the sum of the reciprocals of the sample sizes.
We don't have to come up with that, right?
No. No, but you're going to have to use the formula.
That's fine, we use formula.
Well, I mean, there wasn't a lot that we did to come up with it. It was just, if you plug those things in and do the algebra, you'll get that. It's really not bad. I just didn't want to write all the, there's not even that much simplifying that goes on. It's the sigma squared cancel, essentially, right? There's no sigma squared in there anywhere? No. Okay. All right. So we did the standard normal over the square root of the chi-squared divided by its degrees of freedom. So we get a t, right? Notice, and this is something that pops up as we go through the semester, we're estimating parameters using samples. Every time we make an estimate of a parameter, we end up losing a degree of freedom. We have degrees of freedom that kind of pop up from taking random samples. But every time we have to estimate a parameter using the sample, we lop off a degree of freedom. How many parameters are we estimating here using the random sample, at least for the variance is concerned? 2, right? How many degrees of freedom did we lose? 2, the minus 2 part. This is a recurring theme. Notice the previous one we did the t distribution for the small samples, the same thing happened, right? Jog memory? All right, the same thing happened. All right. To simplify the notation quite often, they give a notation just for this piece. They refer to this as the pooled variance. You're doing a weighted average of the variances, right?
The whole, including the square? Or?
No, just what this part here.
Oh, not even the...
Not even the other part, just the part that's the weighted average. Refer to that as the pooled variance. It's a weighted average idea, right? You're giving the x sample variance this weight. You're giving the y sample variance this weight, and then dividing by the total. The weighted average of the variances. Okay? That's all that piece is. And then the notation for this is I'll use an s squared sub p. Okay? All right. So what, again, notice that this bottom part is really what your standard deviation is, right? Now it looks like we've done x bar minus mu over standard deviation, right? So this is the part that's giving you your helps with your margin of error piece. So when you do the confidence interval for mu1 minus mu2, you'll have an x1 bar minus an x bar minus a y bar, I should say. No, I'm using 1s and 2s again. Never mind. It doesn't matter if you use 1s and 2s, x's and y's, it doesn't matter. You'll subtract off your t on n plus m minus 2 degrees of freedom for alpha over 2. You'll use the t value as opposed to the z value. And then you'll multiply by SP, because I'll do the square root of the pool variance, right? And then times your square root of, I ran out of room. Your square root of 1 over n plus 1 over m.
Is it S3?
I took the square root of it. I took the square root of the squared, so it went away. So SP will just be the square root of the pool variance. It's that piece with the square root in it.
So the S.
Wait, isn't that a plus?
Yeah, it is. Thanks. Yeah, Grace.
So the SP times the square root of 1 over n plus 1 over m is the same thing as that whole value?
Yes. It's just a shorthand way to write it.
Including the square root?
Yeah, because the square root of SP squared would be the square. It is the product, right? So you just do the square root of that product, or the square root of that piece and the square root of that piece. It's just splitting up the square root of the products. So let's see about doing one of these. So I do one then not. Let's do 6.3-2. See if I can get the numbers pulled up here for you. Not connect.
It's coming back.
Whoa, that was weird. Was I shaking that badly? There we go. It's actually the right direction, too.
We're just writing some
Yeah, just the numbers again, that's fine.
We are ready?
Well, if you want to know the numbers, I would write the numbers down. Or if you have your book, you can just look at your book.
Why are there 8
So many Y's.
If I'm going to use Excel, why do I care how many Y's there are?
Fair point, but I don't have Excel.
Well, you know what? That's it.
Is that mine?
No, it's mine. And it's the statement.
I know, aren't they?
I know, they're so cool.
Yeah.
Whoa, hit my
That one's on you.
Wow, it was bad. Hit me right in the
These are like the coolest erasers I've ever had.
I know, and it works so well.
Mhm.
I wonder where we got them.
You can.
No.
I don't know, but I do have a few people who are writing them down, which is why I'm waiting.
No, I wasn't
Well, that's fine.
suggesting that we can move on. I was just asking if you like.
It sounded like you were being a little demanding.
I mean, I can be. At that moment in time,
She was.
She was, I know.
She was just trying to act like she wasn't, but she was.
We got them? If who's getting them? Megan's almost there. Ashlyn, did you get them?
Faster.
Michael, you know.
Why would he start now?
Wait, how old were you? Yeah.
There we go. All right. Come on, Excel. So let's see. We've got 644. I have to make sure I don't go too fast for the keypad.
The cash over your fingertips too quick.
Told you. If I start going faster, it hates it.
You already said it, you're been out of business.
I could not really care any less. Why does it keep doing the 9 twice? Stop it! Man. All right, did I get him typed in right that time? All right, so it was the first 5 were the X's, so we want a keyboard anyway. Wow, I'm just a mess. It's fine. Go away. Go away. All right, here we go. Average the first 5. And average of the last 8. If I type them in the same way, or yes? I depend on you guys to check on me, because I'm pretty incompetent.
So am I, so I'm
Okay, so now this is actually important for this piece. We have to pool the variances, right? So we don't want to use the standard. I mean, if you use the standard deviation command, you're going to want to square it to pool the variances. Or you should be able to use the variance command in Excel as well. Before we just did the standard deviation and used it and divided by the square root of n, right? But if we're going to pool the variances, we actually really need to do the variance, which notice the second and third ones on the list have a var.p, var.s, and again the .p is for population, .s is for sample, just like it is before. You're never going to use the .p.
everybody is there using that. It's just the entire package.
Yes.
Why do they even program that?
I don't know. I mean, all you have to do is, if you took the sample one, you would just have to multiply it by n minus 1 and divide it by n. I mean, that's the only difference between the two. So, I have no idea why. Honestly. Especially when most of the stuff that you're doing are continuous distributions anyway. So, you're doing a discrete sample, a random sample, to find a variance to estimate the population's variance. Why in the world you would have a population variance command when you're doing a continuous distribution is beyond me. I don't know why it's in there. Completeness, I suppose. Could be. Not me. I do. Absolutely.
Senior brother.
All right. So we need to pool those, right? I have to pool this variance with this one. Okay. So to do that, I need to do what? Yeah, so the pooled variance is actually under the square root, right? So if I do it that way, but I could do it at once. Depends on if you want to do the pooled standard deviation or the pooled variance, or whatever you want to do for the formula. But the formula for the pooled variance is what? N minus 1, which in this case will be Yeah, 5 minus 1 to the 4, right? Or if you wanted to use the commands, you could do the count command again. I mean, this is... And this would work for... I mean, it's not hard to count them in this case, but you could use the count command, right? I'm going to need an extra parenthesis in here, though. And then what do I multiply that by? I think that one, right? What the other variance was?
I don't know.
And then you add that to
7, right?
It's just the variance of
I just calculated the variance, so it's just the variance, yeah.
I'm assuming the other one was the 4,000.
This one? Yeah, I'd assume that too. Yeah. That's pulled variance, right? Weighted average, again, idea. That help?
It's a mess.
Yes,
So why isn't the full variance just the average?
because it's a weighted average. We're giving the one with 8 in the sample a higher weight than the one with 5. 5 plus 8 minus 2. Yeah. I mean, really, the weights come from the fact that we have to adjust with those constants to make the chi-square distribution. But it really does turn out to be a weighted average in that sense. All right. So that's our variance. So to find the t's that we want, this problem asked for a 90% confidence interval. So we want to use that t inverse command as a two-side. Now this is, I believe if you do the 2t, you can get the t that you need for both sides at once. Let's see if that works. So the probability we want is 0.1, and the degrees of freedom is what? 11? 1.795. Now, I didn't use this command last time, so let's see if it matches what the other command would be, doing what we did last time. It was a 90% confidence interval, so the probability would be 0.1. So last time we did what? We said we went to the cumulative probability and what was left off from the right tail, right? So we would have used a 0.95 here with 11 degrees of freedom. You get the same value. So you could use that 2t as well, the two-tailed one, whichever one you want to use. So the difference between the two is that for the two-tailed, you put in the alpha, and it'll give you both tails. It'll give you the plus and minus, right? It gives you the plus, and you know that you have to use the minus, right? So that's the t dot inverse, or t dot ind dot 2t. So what that's doing from a graphical perspective is, again, this problem wanted the 90% confidence intervals, so that leaves 10% on the tails, right? So each tail is divided in half. The 1.759 and change, whatever that happened to be, would be your right one, and then your negative one will be your left one. Teaching for this many years, I have to think about left and right anymore because I said right one and left one. This is my left hand and my right hand. So outside of class, I actually have to think about which way is left and right now because I say it backwards so many times because I'm in front of the room. No, that I do correctly, but Sometimes I do have to think what the difference is for my left and my right when I'm thinking about it.
So this is, what is the number that we got? For the next one?
So then, do you want the actual number? That one? Or you're asking me what I got? What does it mean? Okay. So again, if we think about the t distribution, it's at 1.759, whatever that was, and then the negative 1.7959 over here. It's those endpoints for your t distribution, like the z's were.
Yeah.
That's what those are.
And what does that mean for the data? Like that just tells you what the.
So what it does is it tells you for the t distribution that up here there's 5% and down here there's 5%.
So we still have the
Yeah, the mean has to be in the middle of those. Yeah. But remember, for these values they're standardized. So we still have to multiply that by the standard deviation and add and subtract it from the samples. So sample means. Right? This is assuming that your mean is 0 here. And we have to do the adjustment to fit the distribution that we have from the sample.
So that's the one into the function.
Yes. Right.
And we're using the
Why we use t? Because these samples are small. They're so small and the variances are unknown.
I was going to write that down because you said over and over again.
Yep. There might be problems in the book that it tells you that the variance is known, but in practical purposes, the variance is not going to be known. So you're going to have to estimate the population variance. So basically, it really does split into two groups. Large sample, use Z. Small sample, use T.
Okay.
But from a theoretical standpoint, if you know the variance, you would still use the Z. But you're never going to, in practical terms, you're never ever going to know the population variance before you start. And in practical purposes, you'll never ever know the population variance for certain. Ever, no matter what you do. Never. How could you know what the entire population variance is at any given time? Well, then the variance is 0. So all of this would be really, really moot. It's moo. Like a cow's opinion. It doesn't matter. It's moo. Still having friends, but yeah. All right. So let's finish this off now, since we have 4 minutes. What? All right. I say things that aren't words all the time. Pardon me.
God bless you.
Whew. All right. So to get your lower bound, the first thing we need to do is take the difference of the two means, right? Your x bar, which is here, and your y bar, which is here. And then subtract. Your t value is what gives you that margin of error for the standard t distribution. So then we need to multiply it by the square root of, I got to do the pooled variance, and then times the sum of those reciprocals. So I'll do 1/4. I'll just type it in this time. 1/4 and 1/5 and 1/8.
So, I know I already asked this, but I don't know why. SP is not square rooted, right? The S sub P.
S sub P is square rooted. I did S sub P squared over there. I didn't put the square root in here.
Okay, S sub P squared.
So SP and SP squared are just like S and S squared.
So we're just using that bottom piece. When we're just using that bottom piece, we're not using the top.
Remember, the bottom piece is what gives us the standard deviation piece.
Yeah.
So,
So we just need standard deviation of the curve.
yeah. So when we found the t distribution, we would have this essentially equal to the t value that was over here, and we're solving for this, just like we did with the single variance, the single population mean case. So this part here is the confidence interval piece that we're looking at.
Right.
Yeah. All right, so back over here again, sorry. If I hit, are we ready for me to hit enter on this?
So the square root is, how's the SP under it times?
So the square root, because I didn't take the square root here.
Right.
SP assumes that I took the square root of the number.
Okay.
So that's why I put it inside here, because I didn't take it here. It has that whatever number this is has to be square rooted at some point, whichever time you do it. All right. So now if I go back up here. Then change that to a plus sign. So you need to see the formula again, Megan.
And no, I don't
Okay,
think so.
okay.
Just add that to the rate.
Yeah, I just changed the minus sign to a plus is all I did. Okay, so before you go, what does this tell me about the means of the population means? Is, from what we just computed, can we tell whether or not there's a difference between the population means?
No.
Why?
Because you're at
Okay. So this is a confidence interval for the difference of the population means. Can I say for certain one is bigger than the other based on these values? No, because sometimes some of them are negative and some of them are positive, right? Remember, before we start this whole process, what we're calculating is an interval that's likely to contain the true value. Well, 0 is just as likely as anything else that would be in there. All right? So we would not conclude that the means are different. The population means are different. That's a conclusion that we could make from here. There's not enough evidence to conclude that the population means are different. Because 0 is in there, right. The difference might be negative, the difference might be positive. We can't tell. All right. Have a good one.
Okay, so you're still going to be here after 3?
Yes, I will be here.